The title of this presentation is Impedance Network-Based Oscillatory Stability Analyzer, a tool for small signal stability analysis of next-generation power systems. This presentation is prepared by Professor Xiaorong Xie and Dr. Shair from Tsinghua University. We know that impedance-based analysis has been widely used and studied for the small signal stability analysis of power electronic devices and modern power systems with high penetration of power electronic converters. The power electronic converter-based devices, for example, wind turbines and solar photovoltaic inverters, are considered as black box devices, which means that the control structure and parameters are usually unknown. The impedance has to be measured for these black box devices. Characteristics of the emerging oscillation are highly dependent on system operating conditions, which means that if the system operating condition changes, the impedance has to be remeasured and the stability analysis has to be reassessed. Considering these challenges, we have developed a software tool to perform the impedance modeling and analysis of any power electronic device and a large power system with different power electronic devices. Considering the black box characteristics of these devices as well as the operating condition variation. The tool consists of 3 modules, where we have the first module, which is based on collection of system data. In this module, we input the data, which is network topology, for example, the other known parameters of the system, transmission lines, or other system parameters that are already known and fixed. And we establish a set of evaluation operating conditions, the operating conditions at which the devices and the system would operate normally. This can be filtered out by setting some constraints, for example, the terminal voltage and capacity constraints, which will be discussed later in the next slides. Module 2 is to construct operating point variable impedance model. This can be done by hardware-in-the-loop measurement of fixed operating point impedance model for each system component at typical operating points. We have already developed a method which requires impedance model at a few typical operating points, and by using those impedance models calculated at those operating points, we can establish an expression for the variable operating point impedance model. Once we have filtered down the total number of operating conditions to a finite number of operating conditions, for example, 200, 300, or 400, finite number of these operating points, we can do this process on each and every operating point to get the stability region, and we would know that under what set of operating conditions the system would be unstable, and the region can be marked easily. For each operating condition, we first compute the power flow, then we compute the impedance model at each operating point, then we construct the impedance network model based on the system topology. We connect all the individual impedances of different devices based on the system topology. Then we can use the aggregated impedance network model and stability analysis, and then a stability region can be assessed, can be analyzed. We would know that under this region the system would be unstable. I'll briefly talk about a little bit of background of this tool and also different modules and how it would work. We know that for a grid-tied voltage source converter, it would have a specific converter control structure, and which in this case, for example, we have inner current control loops and other voltage control loops. If we know the control structure and parameters, it is easy to get 2x2 impedance or admittance matrix but we can just plug in the values, the parameters, and the structure according to the structure to get the impedance model. However, this is not the case for a practical system. We can inject the small current and voltage signals into the point of common coupling. In this way, we can get the impedance model of power electronic converter. In this case, we have developed an experimental setup where we have impedance model measurement device. This basically a signal injection or identification device, we can say, to get the impedance model of this wind turbine controller, or it can be other power electronic device. We can see that these are the impedance models that we obtain for different types of controllers from different manufacturers. The control structure and parameters of these controllers are unknown. These are basically black box models. The main challenge in this kind of method is that the impedance model that we obtain is only valid for one operating point at which we injected the signal. So if the operating condition changes, the impedance model would be different. For example, we can see that these are the plots for two elements of the impedance matrix, Y11 and Y12. We can see that the black curve is the one operating point where we have a specific impedance model. And if the operating point slightly changes, like for example, the current changes and the voltage changes, the impedance model is different. This indicates that the operating point variation should be considered. To account for the operating condition variation, we have developed a method which this paper has been published recently in IEEE Transaction and Power Electronics. The elements of the impedance matrix for this Yij can be related to the operating point vector. This is X is operating point vector, which consists of nothing but current and voltages. And the Aij and A0, these are the matrices. These equations can be solved and the impedance model can be obtained if we have the impedance model for 10 operating conditions, for 10 typical conditions. This could be different for different systems and different devices. For a few typical operating conditions, we first get the impedance models and those conditions. Then we can solve these equations by using those available measurements. The main point is that first we can get a measurement-based impedance model at some typical operating points. Then we solve these variables. After that, we establish a variable operating point impedance model, or NDA, and nearly decoupled admittance model. That the results we can see almost the same. Once we've got the admittance model at different operating points, now the challenge is how do we know the number of operating points, because we don't know how many operating points we need to check. For this one, we can use some constraints, for example, the voltage and capacity constraints. This is constraint for the capacity, and this is constraint for the voltage. For example, the voltage has to be bounded between the lower and the upper limits. It should not exceed. If these two constraints are valid, it means that the power electronic device is operating under normal conditions. So all the operating points for which these two constraints are true, those operating points can be considered as a plane of those operating points. For example, this D can be set as the operating point plane. The number of operating points in this plane would be almost infinite. To get finite number of operating points, basically we can sectionalize, we can divide into a few operating points based on the deviation or the small difference. Here we will get a number of operating points. After that, we can use, actually we don't have to do the stability analysis on all the operating points that we narrowed down. We can use some searching algorithms to approximately determine the stability boundary or region. If we just want to know the region under which the power electronic device or any device or the system would be stable, we just need to check the stability at a few operating points. For the stability analysis, we could use any of the existing methods. We prefer to use impedance network model-based stability analysis by Huaguan Liu. Here we have one case where there is a grid-tied voltage source converter. Basically, these are the same devices, but aggregated several number of voltage source converters with the specific control structure and parameters. The first step is we construct the operating points, and we get the impedance model at these 10 operating points. We got the 10 impedance models or admittance models. By using those 10 admittance or impedance models, we can get an operating point variable impedance model, which is a function of voltage and current, which is actually operating point. So this impedance model is a function of the operating point. Once we have got the variable operating point impedance model, we can do the stability analysis using the methods described in this paper. The stability results can be plotted according to the operating points. For example, the power, the active and reactive powers. First, we plot the critical stability plane for which the damping is 0, so we can see if the system is stable or not. For the operating points at which these are the plane of operating points where the damping is 0, and this is the plane where we can see under some conditions there is oscillation, but this oscillation is stable because it is not crossing the damping, the 0 damping. So this means that under these operating points, there is only one voltage source converter connected with the system. So the system is stable. In this case, we increase the number of voltage source converters, and we can see under these operating points, the damping is positive, which means that under these specific operating points, the system is unstable. And the same goes for here, for 1000 number of voltage source converters. This is the stability region for under different number of voltage source converters connected to the grid. For example, 300 and 600 and 1000. So we can see that the stability region for the 1000 number of voltage source converters is very narrow, which means that this is the most critical, where we have a large boundary of the stability region. So we have 179 operating conditions when n is equal to 1000. So we run the EMT simulations at all these 179 operating conditions. We can see that the results are consistent. This is the round ones are basically stable operating points. All these operating points are stable, and outside these are unstable operating points. So the conclusion here is that the results that are obtained from the proposed method by doing these kind of stability analysis on different operating points has been validated through the EMT simulations. This method has also been applied on the simplified HAMI system, which consists of several wind farms and HVDC lines and conventional turbo generators. This kind of stability region can also be plotted. We can see under which operating condition this kind of system would be unstable, and under which operating condition this would be stable.